Signs of function values. In this lesson, we're going to look at the quadrant of the terminal side of an angle in standard position and see how the quadrant of the terminal side determines whether the trig function for the angle will be positive or negative. We'll start with an angle whose terminal side is in the first quadrant. Let's label this quadrant 1. Now this terminal side could be anywhere in the first quadrant, and what I need to do is to just pick any point on this terminal side other than the origin, and let's talk about the x and y coordinates for this point. Since this point would be in the first quadrant, since we know that all x coordinates in the first quadrant are greater than 0, and all y coordinates in the first quadrant are greater than 0, then we know the x coordinate of this point must be positive and the y coordinate of this point must be positive. We also know that r is the distance from the point to the origin and that r is always positive. So for this first quadrant angle, which I will just call theta, if I find the sine of theta, that will be y divided by r. Y is a positive number, r is a positive number. When I divide a positive number by a positive number, I will get a positive number. So the sine of any first quadrant angle will be a positive number because reciprocals have the same sign. Then we know that the cosecant of an angle whose terminal side is in the first quadrant will also be positive because it's the reciprocal of the sine function. Let's look at the cosine function. It equals x divided by r. X is positive, r is positive. Therefore, the cosine of a first quadrant angle will also be positive, as will its reciprocal, the secant. Look what happens with the tangent. We know the tangent equals y divided by x. Once again, I will have a positive divided by a positive, which will give me a positive number. Because the tangent of theta is a positive number, then the reciprocal of the tangent will also be positive. So if I have a first quadrant angle, all 6 trig functions of that angle will equal to a positive number. Now let's see what happens in the second quadrant. I'll follow the same process. My angle in standard position, terminal side in the second quadrant. I'll pick any point except the origin on the terminal side. Now in the second quadrant, x is less than 0, y is greater than 0. So for this point, whatever point that I would pick on the terminal side, because it's in the second quadrant, its x coordinate will be negative and its y coordinate will be positive. And of course we know r is greater than 0. So when I get its trig functions, and let's call this angle theta, and I'm going to put a Roman numeral 2 to denote that its terminal side is in the second quadrant. I guess I should go ahead and label that second quadrant, shouldn't I? So when I find the sine of my second quadrant angle, y divided by r, my y is positive, my r is positive, which will give me a positive. And of course I know that then the cosecant will also be positive because reciprocals have the same sign. On my cosine of my second quadrant angle, when I take the x and divide it by r, for a second quadrant angle, the x's will all be negative. R is positive. A negative number divided by a positive number will give me a negative number. So if I find the cosine of any second quadrant angle, it will equal a negative number, and so will its reciprocal, the secant. So the secant will also equal a negative number. When I find the tangent, that's y divided by x. Y is positive, x is negative, and a positive divided by a negative will give me a negative. So the tangent of any second quadrant angle will be negative, and the cotangent will also be negative because it's the reciprocal of the tangent. So let's see what happened in that second quadrant. I only had two functions that were positive, the sine and the cosecant, and I had four functions that were negative. The cosine of a second quadrant angle, the tangent of a second quadrant angle, the secant of a second quadrant angle, and the cotangent of a second quadrant angle will be negative. It is important that you know these signs. We will summarize when we get through with the third and the fourth quadrant. So let's look at quadrant 3 now. For my third quadrant angle, I'll call this theta 3 to denote that its terminal side is in the third quadrant. When I pick a point on its terminal side, what do I know about all the x and y coordinates for points in the third quadrant? X is less than 0, y is less than 0. So I know the x coordinate here will be negative and the y coordinate will be negative. And of course, r I know is always greater than 0. So let's get the signs of my 6 trig functions. For the sine of my theta 3, y divided by r, my y is negative, my r is positive, so I will get a negative number, which means also that the cosecant of my third quadrant angle will be negative. For my cosine of my third quadrant angle, x divided by r, my x is negative, my r is positive, so I will also get a negative value, and its reciprocal will be negative. For my tangent of a third quadrant angle, that's y divided by x. That would be a negative number divided by a negative number, which gives me a positive number. So the tangent of a third quadrant angle will be positive, and its cotangent will also be positive because they're reciprocal. So in the third quadrant, the sine, the cosine, the cosecant, and the secant are all negative, and the tangent and the cotangent are all positive. Let's last look at this fourth quadrant angle. We'll call this theta 4. We'll pick a point on its terminal side. Now in the fourth quadrant, we know that all the x coordinates are greater than 0, all the y coordinates are less than 0, and of course we know our r's are all positive. So for this point, its x coordinate will be positive and its y coordinate will be negative. So when we find the sine of a fourth quadrant angle, our y is negative, so we'll have a negative divided by a positive r, which will give us a negative. And of course we know the cosecant then will also be negative. For the cosine, our x divided by r, our x is positive, r is positive, so our cosine function will be positive, as will its reciprocal, the secant. And then let's look at the tangent. We'll have y divided by x. Y is negative, x is positive, which a negative divided by a positive gives us a negative, and the cotangent, which is the reciprocal of the tangent, then would also be negative. So in the fourth quadrant, our negative functions were the sine, the cosecant, the tangent, and the cotangent, and our positive functions were the cosine and the secant. Now let's summarize what we found. There's several ways that you're going to need to know this information, so I have a couple of ways I would like to summarize this. Generally, in the textbooks, you see a coordinate system, and each quadrant is labeled with the functions that are positive in that quadrant. So in the first quadrant, all functions were positive. In the second quadrant, the two functions that were positive were the sine function and its reciprocal. Now I'm going to call the angle theta 2. I'm going to continue to use that little subscript so that you know that that means that angles whose terminal sides are in the second quadrant, their sine function and cosecant functions are positive. For the third quadrant, two functions were positive. The tangent, and I'll put little theta 3's, and its reciprocal, the cotangent, are the positive functions. And then in the fourth quadrant, the cosine, and I'll call that theta 4, and its reciprocal, the secant. Now, it's important for you to realize, for you to know in a quadrant, for instance, in the second quadrant, that the sine function and cosecant function are positive and that all the other functions are negative. In the third quadrant, the tangent function of third quadrant angles and the cotangent function of third quadrant angles are positive and all other functions are negative. In the fourth quadrant, the cosine of fourth quadrant angles and the secant of fourth quadrant angles are positive. All other functions of fourth quadrant angles are negative. And of course, all functions are positive for first quadrant angles. I think it's also important for you to know it by quadrant and to classify it in quadrant 1. All functions are positive, none are negative. For quadrant 2, the functions that are positive would be the sine function and the cosecant function. The functions that are negative for quadrant 2 angles would be the tangent function, the cotangent function, the cosine function, and the secant function. In the third quadrant, the functions that are positive would be the tangent function and the cotangent function, and the functions that are negative would be the sine function, its reciprocal, the cosecant function, the cosine function, and its reciprocal, the secant function. In the fourth quadrant, the functions that are positive would be the cosine function and its reciprocal, and the functions that are negative would be the sine function, its reciprocal, the tangent function, and its reciprocal. Now let's look at another way to summarize this. it's important for you to realize that for the sine function and the cosecant function, these two functions are reciprocal, so that's why I have it in a table like this, that there are two quadrants that these functions are positive in and two that are negative. The two quadrants that the sine and cosecant are positive in are the first quadrant and the second quadrant, and the two quadrants where they are negative are the third quadrant and the fourth quadrant. For the cosine and secant function, there are two quadrants that the cosine and secant are positive, first quadrant and fourth quadrant, and the two quadrants where they're negative are second quadrant and third quadrant. For your tangent and cotangent functions, they are positive in the first quadrant and the third quadrant, and they are negative in the second quadrant and the fourth quadrant. In the work that we do in trig, there are times when we will talk about the quadrants. For instance, we might say which functions are positive in the third quadrant, and you would be expected to know that the tangent function and cotangent functions are positive of angles whose terminal side is in the third quadrant. But sometimes, instead of talking about the quadrant, we'll talk about the function, like the cosine function. And you may need to know in which quadrants is the cosine function positive and in which quadrants is it negative. So it's important for you to learn these sine values in terms of the quadrant, but also in terms of the function. And so that's why I put it in a table like this, was so that you would think of it in terms of the function. A final summary, and this appears in most books, and you might want to copy this down. If theta has a terminal side in quadrant 1, then all the functions are positive. If theta has a terminal side in quadrant 2, then the sine is positive, the cosine is negative, the tangent's negative, the cotangent's negative, the secant's negative, and the cosecant is positive. If theta has a terminal side in quadrant 3, then its sine is negative, its cosine is negative, the tangent's positive, the cotangent's positive, the secant's negative, and the cosecant's negative. For an angle whose terminal side's in the fourth quadrant, the sine will be negative, the cosine positive, the tangent negative, the cotangent negative, the secant positive, and the cosecant negative. Now let's look at some problems where we'll need to know where these functions are positive and negative. It says identify the quadrant or quadrants satisfying the given conditions. In A, we want to find the quadrant of the angle when we know that the sine of theta is greater than 0, which means that the sine is positive, and that the cosine of theta is less than 0, which means the cosine is negative. Well, to do this, let's think. The sine of theta is positive in the first quadrant and the second quadrant. The cosine of theta is negative in the second quadrant and the third quadrant. So in which quadrant do both of these things occur? Well, it would be the second quadrant. Theta would be in quadrant 2, because for an angle whose terminal side was in the second quadrant, its sine would be positive and its cosine would be negative. For B, we know that the sine of alpha is less than 0, which means the sine is negative, and the sine is negative in the third quadrant and the fourth quadrant. Now, let's see. This says the tangent of alpha is greater than 0, which means the tangent is positive. So where is the tangent positive? Well, it's positive in the third quadrant. It's also positive in the first quadrant, but we know alpha can't be in the first quadrant because we know the sign of alpha is negative. So alpha in this case would have a terminal side in quadrant 3. On the C problem, the tangent of beta is less than 0, which means that beta would have to be in the second quadrant or the fourth quadrant. But we also know that the cosine of beta is greater than 0, which means that beta has to be in the first quadrant or the fourth quadrant. So the quadrant where the tangent is negative and the cosine is positive would be the fourth quadrant. So beta has a terminal side in the fourth quadrant. For D, we have the sine of gamma is less than 0. Let's see, the sine's negative in the third and fourth quadrants. The cosine of gamma is greater than 0. The cosine is positive in the first and fourth quadrants. So the quadrant where the sine is negative and the cosine is positive would be the fourth quadrant. So gamma has a terminal side in the fourth quadrant. And last, the only information we have is the tangent of phi is greater than 0. Well, that would either be that phi has a terminal side in the first or the third quadrant, since that's all the information we have. Let's look at one last type of problem. For this problem, it says, give the sign of the 6 trig functions for each angle. Well, what we have to do is first figure out where the terminal side, which quadrant the terminal side of each angle is in, and then we have to know the signs of the functions for the angles whose terminal sides are in that quadrant. So we'll start with 121 degrees. If that is in standard position, what quadrant? It would be in the second quadrant, wouldn't it? So what do I know about the sine function of second quadrant angles? It's positive, as is the reciprocal, the cosecant. The cosine function is negative, as is its reciprocal, the secant. The tangent function of 121 degrees would also be negative, since the terminal side's in quadrant 2, as would its reciprocal, the cotangent be. For the B part, we have an angle that's a negative 286 degrees. Well, if we draw that in standard position, we know negative goes clockwise, so I'd go 90. 90 more would be 180. 90 more would be 270, and I know that all the way around is 360, so I know that negative 286 would have a terminal side in the first quadrant, don't I? And so what about all the functions of this angle? They would all be positive. And I picked this example to point out that whether the angle is positive or negative has nothing to do with whether the functions are positive or negative. What is important is where the terminal side of the angle is. And in this case, even though it's a negative angle, because its terminal side is in the first quadrant, if we picked any point on that terminal side, then the x-coordinate would be positive, the y-coordinate would be positive, r would be positive, which would make all the functions positive. For 322 degrees, where's the terminal side? 90, 180, 270. it would be somewhere in the fourth quadrant, right? So in the fourth quadrant, the sine function is negative, as is the cosecant function. The cosine of 322 degrees would be positive because the cosine and the secant of fourth quadrant angles are positive. And what about the tangent and the cotangent of fourth quadrant angles? They're negative, aren't they? Last, we'll look at 195 degrees. Which quadrant is its terminal side? 90, 180, be in the third quadrant, wouldn't it? So the sine function of 195 degrees would be negative, as would its cosecant. The cosine function in the third quadrant is negative, so the cosine and secant of 195 degrees would be negative. And which functions are positive in the third quadrant? The tangent and the cotangent. So the tangent of 195 degrees would be positive, and the cotangent of 195 degrees would be positive. These last problems are examples of why it's important for you to know the signs of the trig functions for the different quadrants. So make sure that you learn where these functions, which quadrants these functions are positive in, which quadrants they're negative in, and for each quadrant that you know which functions are positive and which functions are negative. This completes this lesson. Please rewind the tape before you return it. Thank you. The Pythagorean identities and the quotient identities. In this lesson, we'll derive the Pythagorean identities and the quotient identities, and then we'll work some problems that require that we know those identities and the reciprocal identities. Let's first look at the Pythagorean identities. We begin with the assumption that xy is a point on the terminal side of an angle theta in standard position. And of course we know then that x squared plus y squared equals r squared is the Pythagorean relationship in x, y, and r. And what we'll do first here is we will take this equation and we'll just divide both sides of the equation by r squared. Now what we get is x squared over r squared, which we could write as x divided by r squared, and here we get y over r squared, which we could write like that, and of course r squared divided by r squared equals 1. Now, which trig ratio is x over r? We know that x over r is the cosine. So this is the cosine of theta, since that's our angle, squared. Y over r is the sine of our angle theta squared, equals 1. Now we know from a previous lesson that when we mean cosine theta times cosine theta, which is what cosine theta squared means, we agree in trig that we'll put that square right there. So this first identity is cosine squared theta plus sine squared theta equals 1. Now what we will do with that is we can take this identity and solve for cosine squared theta by subtracting sine squared theta from both sides, and we get cosine squared theta. Of course, sine squared theta minus sine squared theta adds to 0, and on the other side we have 1 subtract sine squared theta, which is just 1 minus sine squared theta. So there is another form of this Pythagorean identity, and the last thing we'll do is we'll take cosine squared theta plus sine squared theta equals 1, and this time we'll subtract cosine squared theta from both sides. And of course those add to 0, so we get sine squared theta equals 1 minus cosine squared theta. So we have 3 different forms of this identity, and you need to know all 3 of them. Cosine squared theta plus sine squared theta equals 1, cosine squared theta equals 1 minus sine squared theta, and sine squared theta equals 1 minus cosine squared theta. Okay, this time we start with the same xy point on the same angle theta, but this time instead of dividing through by r squared, let's divide through by x squared. And so x squared divided by x squared is 1. We'll have y over x squared, and on the other side of the equation we get r over x squared. And of course we know y over x would be the tangent of theta, so this would represent tangent squared theta, and r over x is the secant of theta, so this would represent secant squared theta. So there's another Pythagorean identity, and there are 2 other forms of this one. The first thing I will do with this equation is subtract 1 from both sides. Of course, 1 minus 1 adds to 0, and that leaves me with tangent squared theta equals secant squared theta minus 1. And then for this same relationship, this time what I will do is I will subtract tangent squared theta from both sides. And so I end up with 1, and of course tangent squared theta subtract tangent squared theta is 0, and on the other side of the equals I will have secant squared theta minus tangent squared theta. So that's 3 forms of this Pythagorean identity, and once again you need to know all of them. 1 plus tangent squared theta equals secant squared theta. Tangent squared theta equals secant squared theta minus 1, and 1 equals secant squared theta minus tangent squared theta. we have one more set of Pythagorean identities, and we'll start with the same angle theta with xy on its terminal side. And this time, let's divide everything by y squared. And what we get is x over y squared plus y squared over y squared is 1 equals r over y squared. And of course, x divided by y is cotangent. So this would be cotangent squared theta plus 1 equals, and r over y is cosecant. So on the other side, we'll have cosecant squared theta. Now, let's get the two other versions of this. The first thing that I will do is I'll subtract the 1 from both sides. That will leave me with cotangent squared theta equals cosecant squared theta minus 1. And taking that same relationship, this time I'm going to subtract cotangent squared theta from both sides, and I will get 1 equals cosecant squared theta minus cotangent squared theta. And be sure you know these three different identities. Cotangent squared theta plus 1 equals cosecant squared theta. Cotangent squared theta equals cosecant squared theta minus 1. And 1 equals cosecant squared theta minus cotangent squared theta. Now let's look at a summary of all 9 of the Pythagorean identities. You need to copy all of these down. You need to make sure that you know them. In general, if in your work you have a sine squared theta plus cosine squared theta, then you're going to replace it with 1 because 1 is easier to work with. For some of these other forms, there are times when you will have a 1 minus cosine squared theta and you'll replace it with sine squared theta, but then there are times that when you have a sine squared theta, you'll want to use 1 minus cosine squared theta. So it's very important when you learn these 9 identities that when you see this, you know it equals to sine squared theta, but when you see sine squared theta, that you know it equals 1 minus cosine squared theta also. I suggest to you that for each of these, that you put the left side of the equation on one side of an index card and the right side on the other side of the index card, and learn both sides. When you see one side, be sure that you know what the other side is. The last identities that we're going to look at in this lesson are the quotient identities. So let's see how we can derive the quotient identities. We'll start with sine theta divided by cosine theta, and what we will do is for our angle theta in standard position, if we pick a point on the terminal side, xy, once again, then we'll think that we could find the sine of theta by taking that y coordinate and dividing it by the r coordinate, and the cosine of our theta, we could get that ratio by taking the x coordinate of our point and dividing it by r, where of course we know r is the square root of the x squared plus y squared. Now let's simplify this fraction. When we divide fractions, we multiply by the reciprocal of the denominator. So we'd have y over r times the reciprocal of r over x times the reciprocal of x over r, which would be r over x. And of course the r's divide to 1, so we're left with y over x, and which trig function do we get of theta if we take the y coordinate and divide it by the x coordinate? Well, that's equal to the tangent of theta, isn't it? And so our quotient identities are that sine theta over cosine theta equals the tangent of theta, and since we know that tangent and the cotangent are reciprocals, the reciprocal of sine theta over cosine theta would be cosine theta over sine theta. So these are our two quotient identities. Be sure that you write those down. There will be times when you will see the sine of theta divided by the cosine of theta, and you'll replace it with the tangent of theta, and there will be times when in place of the tangent of theta you'll use sine theta over cosine theta. So you will need to know both of these. Once again, I suggest that you take the left side, put it on an index card, and put the right side on the other side of the index card, and be sure that you can identify those identities looking at either side of the index card. All right, now we're going to work some problems, and for these problems you're going to need to know your Pythagorean identities and your quotient identities, but also we will use your reciprocal identities. So if you haven't studied the reciprocal identities, you might want to view that lesson before you attempt these problems. Use identities to find the indicated function value. Well, what they want us to find here is the cosine of alpha, and what they're telling us is that the sine of alpha equals negative 1/3, and they are also telling us that alpha is in quadrant 3, so it's a third quadrant angle. For the problems in this lesson, I'm going to work them in two different ways. I'm going to work them the way that I think is easier first, but then I'll work it a second way because most textbooks work it both ways, and some teachers require that you know how to work it the other way. So this is how I would work this. To start off, noticing that alpha is in quadrant 3, I know that in the third quadrant, if I pick a point on the terminal side of alpha, xy, that my x is less than 0 and that my y is less than 0, because in the third quadrant all the x and y coordinates are less than 0. Of course, I know always that r is greater than 0. So when I know that the sine of alpha equals negative 1/3, I know that the sine of alpha is equal to the y coordinate divided by r. Well, if I see a negative here, the way that I have a negative there is either for the numerator to be negative or for the denominator to be negative. So I know in this case that it is my numerator that must be negative because my y is negative and my r is positive. So by knowing that the sine of alpha equals negative 1/3, I know that my y coordinate could be negative 1 and that my r then would be 3. And so when I get ready to find the cosine of alpha, I know the cosine of alpha is x divided by r. So what I need to do is figure out what x is. Well, because of the Pythagorean relationship, x squared plus y squared equals r squared, then I know that x squared is equal to r squared minus y squared, and I know then when I extract roots that x equals plus or minus the square root of r squared minus y squared. In this case, since alpha is in the third quadrant, I know my x is negative. So I will find my x, and once I know my x, I know my r is 3, then I will have the cosine of alpha. So I think I'll find my x right down here. I know x is negative. My r is 3, so that would be 3 squared. Subtract my y is negative 1. So I'll have minus 3 squared is 9. Subtract negative 1 squared is 1. So I have minus the square root of 8. Now we'll simplify that, won't we? We know that the square root of 8 is the square root of 4 times the square root of 2, and we know the square root of 4 is 2. So that would be the negative 2 times the square root of 2. So the cosine of alpha is negative 2 times the square root of 2. Now we don't usually leave that negative in the numerator. It's not that it's wrong, but we would usually put it out front, and we would have 2 times the square root of 2 over 3. And of course we know that for an angle in the third quadrant, its cosine is supposed to be negative, so we were expecting it to be negative. Now I'd like to work this problem using the Pythagorean identities that we just derived, and possibly quotient and reciprocal, just so that you can see a different way to work it. I don't think it's as easy as what we just did, but some of you will need to know it this way. I start with the very same information, but when I'm given the sine of alpha, it is fairly easy for me to find its reciprocal, the cosecant of alpha, or to find its Pythagorean identity relationship function, which is the cosine of alpha. So what I'm going to do here is work off of my Pythagorean identity. I know cosine squared alpha equals 1 minus sine squared alpha, don't I? And of course I just want the cosine of alpha, so the cosine of alpha would equal to plus or minus the square root of 1 minus sine squared alpha. And now the next thing that I'm going to do is I'm going to decide whether the cosine of alpha is positive or negative. And when I know alpha is in the third quadrant, I know that the cosine of all third quadrant angles is negative, so I'll put a negative there. And my next step here will be that in place of the sine of alpha, I'll put that value. So I need to take negative 1/3, and I need to square it. So let's see here what I get. I'll have 1 minus. Of course, when I square a negative, I get a positive. 1 squared is 1, and 3 squared is 9. And so now I get to work with some fractions. We need a common denominator, so we'll write the 1 as 9 over 9. And so 9/9 subtract 1/9 would give us 8/9. And then when we simplify, we'll have the square root of 8 divided by the square root of 9. The square root of 8 we know is 2 times the square root of 2, and the square root of 9 is 3. So you see we get the very same value using this Pythagorean identity. Now let's look at another problem. I call that first method that I used on that last problem the XYR method. So if that's what I'm talking about, it means that if you're given one trig function, then you know 2 of those values and you can find the third one. For this problem, we are supposed to find the sine of theta, and we know that the secant of theta equals -3, and we know that theta is in the second quadrant. So using that XYR method, I know if I want to find the sine of theta, that it is equal to y divided by r. So I need to figure out what y is and what r is. And when I'm given the secant of theta equals -3, I know that the secant of theta is r over x. Well, in this case, since it's negative, of course, I need to figure out whether my x's and y's are positive or negative. I know that my r is positive, and that's why I have to know the quadrant. So r is greater than 0. In the second quadrant, what about x and what about y? Well, in the second quadrant, x is negative, x is less than 0, and y is positive, so y is greater than 0. So if I know the secant of theta is negative, then since r can never be negative, I know it's the x that's negative. So when I write this as a fraction, writing -3 as a fraction, I'm going to write it as 3 over 1, and that of course is just the number 3. But to make it negative, I know the x has to be negative. So the secant of theta is 3 divided by -1. So if I want to find my y in this case, and I will get the sign first, it's positive, and so I'll write the positive. I know that since y is a leg, that the way I find a leg is to say r squared minus the other leg squared, which would be x squared in this case. So my y would equal to 3 squared minus -1 squared, which would be 9 minus 1, which would be the square root of 8, which is 2 times the square root of 2. So my sine of theta in this case, my y equals 2 times the square root of 2, and my r in this case is 3. So that would be my sine of theta. Now let's look at this. Instead of using the x, y, and r method, let's use some of those identities. Okay, if you're asked to find this using the Pythagorean identities or the quotient identities or the reciprocal identities, when you see that you're given the secant of theta, you should know that there are two things that you can find fairly easily. The first thing would be the cosine of theta, which would simply be the reciprocal. The second thing would be the function that is related to the secant in the Pythagorean identity, which would be the tangent. So, given this information, we can either find the cosine or the tangent. Now, I think it would be easier here to find the cosine. So, that's what I'm going to do first. The cosine of theta, since I know it's the reciprocal of the secant, I just have to write the reciprocal of -3. Now remember that reciprocals have the same sign, so the reciprocal of -3 is -1/3, so the cosine of theta is -1/3. Now since I have the cosine, I can find the sine of theta by using the Pythagorean identity that says that the sine of theta equals, sine squared theta equals 1 minus cosine squared theta. So I know then that the sine of theta equals plus or minus the square root of 1 minus cosine squared theta. So my first thought here will be, is it plus or minus? And remember what tells us whether the sine of theta is positive or negative. It's the fact that theta is in the second quadrant, which of course means that the terminal side of theta is in the second quadrant. And for any angle whose terminal side is in the second quadrant, then we know its sine function is positive. So this will be positive. So I will say 1 minus, I will take my cosine of theta, which is -1/3, and I will square that. So I will have 1 minus, once again a negative squared is a positive, 1 squared is 1, and 3 squared is 9. And so my 1 is 9/9. I will subtract the 1/9 from it. I will get the square root of 8/9. And then when I simplify, I will get 2 square root of 2 divided by 3. In these last two problems, it really has not made a lot of difference whether we use the x, y, r method for finding the trig function we were looking for, or if we use the Pythagorean identity. In the next problem, we will be given the trig function, one trig function for an angle, and we'll be asked to find the other 5. I think you'll see that it makes a big difference when we're looking for all the trig functions of an angle. Find all the trig function values for B. And we're told that the tangent of beta equals 4/3 and that beta is in quadrant 3. Well, what I'm going to do here is first identify what x is and what y is and what r will be. Since it's a quadrant 3 angle, r is always greater than 0. But what about your x and your y in the third quadrant? Well, they are both negative. So x will be less than 0 and y will be less than 0. So if we're told that the tangent of beta equals 4/3, we know that the tangent of beta is y divided by x, don't we? And so since it is a third quadrant angle, and since the x's and y's are negative, that means that our y in this case must be -4 and our x must be -3. And consequently, we wouldn't write that the tangent of beta was -4 over -3, and negative divided by negative is a positive. We would write that the function value was 4/3. But it's important for us to pay attention to this quadrant and to realize that because it is a quadrant 3 angle, that y would have to equal -4 and that x would equal a -3. Now we can find our r, which of course our r is the square root of our x squared plus our y squared. Our -3 squared gives us 9. Our -4 squared gives us 16. So we'll have 9 plus 16, which gives us the square root of 25, which is 5. So here's what I would do with this. The sine of beta is y divided by r. So that would be -4 divided by 5, which is -4/5. The cosecant of beta is the reciprocal of that, so that would equal -5/4. To find the cosine of beta is x divided by r, so that would be -3 divided by 5, which would equal -3/5. And then to find its reciprocal, the secant of beta, that would equal -5/3. Now I have 4 of the functions, don't I? I know the tangent is 4/3. I'll go ahead and find the cotangent. Probably should have done that first. That's the easiest one to find. If the tangent of beta is 4/3, then the cotangent of beta is 3/4. So I have this function, tangent, cotangent, sine, cosecant, cosine, secant. I have all the functions of beta. Let's work that problem again, and let's use reciprocal identities and Pythagorean identities. Okay. Now, using the reciprocal identity, if I know the tangent of beta equals 4/3, then I know that the cotangent of beta equals its reciprocal, which is 3/4. Now, the next thing that I will find is the function that is related to the tangent in the Pythagorean identity, and that would be the secant of beta. So since I have the tangent, I can find the secant because I know that the secant of beta equals 1 plus tangent squared of beta, and that is not just the secant, it is secant squared of beta equals 1 plus tangent squared of beta. I'm dropping my squares today, aren't I? And so to find the secant of beta, then I know that the secant of beta is equal to plus or minus the square root of 1 plus tangent squared beta. And so what I'm going to do next then is to decide whether this should be positive or negative, and then I'll replace my tangent of beta with that 4/3. And to decide whether it's positive or negative, I'll look at the quadrant. It's quadrant 3. And so for the secant function of an angle whose terminal side is in quadrant 3, I know that it is negative. So this should be a negative. So I'll have minus the square root of 1 plus, and then I'll put my 4/3 in for my tangent of beta, and then I want to square it. So I'll have minus square root of 1 plus. When I square, I get 16/9. So I'll have my minus. I'm going to write my 1 as 9/9, and I will add to that 16/9. So I'll have minus, when I add 9/9 to 16/9, I have 25/9. And then the square root of 25 is 5, and of 9 is 3. So my secant of beta equals negative 5/3. I think the easiest thing to find when I have the secant here then would be the cosine. It's reciprocal. So the cosine of beta then is negative 3/5. So I have 4 of my function values. Now the only 2 that I need the sine of beta, and then I need the cosecant of beta. And it's really up to me, and it's really up to you. If I know the cotangent of beta, then I can find the cosecant. And if I know the cosine of beta, then I can find the sine. I'm going to choose to find the sine using its Pythagorean identity. And I'm going to do that because you tend to work with sines and cosines more than you do with cotangents and cosecants. And so that's what I'm going to choose to use. I will start off with the fact that sine squared beta equals 1 minus cosine squared beta. And then I will say that the sine of beta equals, extracting roots, plus or minus the square root of 1 minus cosine squared beta. And then I will decide whether the sine of beta would be positive or negative. And what that refers to is, if we can go back up here, beta is in quadrant 3, and for the sine of an angle whose terminal side is in quadrant 3, we know is negative. So the sine of beta will be negative. I'll have 1 minus. In place of my cosine, I'll write negative 3/5, and I want to square it. I'll have minus the square root of 1 minus When I square the negative, I get a positive. 3 squared is 9, and 5 squared is 25. I will write my 1 as 25 over 25 and subtract 9 over 25. Well, 25 25ths subtract 9 25ths gives me 16 25ths. And when I simplify, the square root of 16 is 4 and the square root of 25 is 5. So the sine of beta is negative 4/5. I can easily get the cosecant of beta using its reciprocal. It will equal negative 5/4. So let's just look at the work that I've done here using the Pythagorean identities and the reciprocal identities. I found that the cotangent of beta was 3/4. The secant of beta was negative 5/3. The cosine of beta was negative 3/5. And then we found that the sine of beta was negative 4/5. And the cosecant of beta was negative 5/4. So we have all the trig functions of beta. Well, as you can see from the last problem, it didn't matter whether we used the XYR method to find the function values of the angle, or if we used the Pythagorean and the reciprocal identities to find the function values. Obviously, we got the same function values. So it's your choice which method that you use. The thing that you should be able to do, though, is if you are given one trig function of an angle, and you are given the quadrant that the terminal side of the angle is in, or if you're given enough information to figure out what quadrant the terminal side is in, then you should be able to find all the other trig functions of that angle, either using the XYR method or using your Pythagorean identities. Let's look at one more problem like that. Find all the trig function values of omega, and we're given that the cosine of omega is the square root of 5 over 3, and we know that omega is in the fourth quadrant. Well, I will use the XYR method, except that I might as well go ahead. I can very easily state what the secant of omega is. It is the reciprocal, which would be 3 divided by the square root of 5. Now, I don't want to leave it like that, do I? I do want to rationalize. I will multiply by the square root of 5 over the square root of 5, and I get 3 times the square root of 5 over, and of course the square root of 5 times the square root of 5 is 5. So I've got the secant. Now, let's see. I know that because it is a cosine function, that it represents an x value divided by r. And in this case, fourth quadrant, I know that my x is greater than 0. In the fourth quadrant, I know that my y is less than 0. And of course, it doesn't matter what quadrant, r is greater than 0. So in this case, my x is a positive square root of 5, and my r is a 3. And so the next thing that I'm going to do is to find y, and I know that my y is negative because the terminal side of omega is in the fourth quadrant, and all the y coordinates are negative in the fourth quadrant. So I'll have a negative, and to find my y, I will take my r and square it, and subtract from that my x squared. Well, 3 squared is 9. Subtract, and the square root of 5 squared is 5. So I get minus, subtracting 5 from 9, I get 4. So I get a minus 2. So my y is minus 2. So since I have all my x, y, and r values, I should be able to find all of my trig functions. I've got the cosine and the secant. Let's find the sine. It's y divided by r, so that would be negative 2 divided by 3, or negative 2/3. Let's go ahead and find the cosecant, which would be the reciprocal, so it would equal negative 3/2. Now, for my tangent equals y divided by x, so my y is negative 2 divided by x, which is the square root of 5, and so I will rationalize. I will go ahead and bring the negative out front, so I will have negative 2 times the square root of 5 over 5. Now, if I want to find the cotangent, yes, I can use the reciprocal of this. That's fine, but I'm going to end up with this radical in the denominator, and I'll have to rationalize. Notice that originally what I had here was that the tangent of omega equals negative 2 divided by the square root of 5. I just did this because I had to rationalize it. Well, when I get ready to find the cotangent, it would be easier to use the reciprocal of this. I know this is just an equivalent of this because I'm just multiplying by 1, but for my purposes, let's put the negative out front, and then let's use the reciprocal. The cotangent of omega would look like that. It would be minus the square root of 5 over 2. So I think I've got all 6 functions: cosine, secant, sine, cosecant, tangent, cotangent. The last thing I'm going to do in this lesson is to rework that last problem using Pythagorean identities and reciprocal identities. And so if you're not interested in seeing that problem worked using that method, you might as well go ahead and rewind the tape. But if you want to see it, well, come on, let's work this problem. Okay, let's see. We've got the cosine of omega equals the square root of 5 over 3. Well, I'll start out the same way. Let's just go ahead and state that the secant of omega equals 3 divided by the square root of 5, which would be the reciprocal, and then we'll rationalize. We'll multiply by the square root of 5 over the square root of 5, which will give us 3 times the square root of 5 over 5. Now, we've got the only reciprocals that we can get with this information. The question is, where do we go from here? Well, for the cosine function, we could find the sine using the Pythagorean identity that relates those two. And with the secant function, we could find the tangent using the Pythagorean identity that relates those two. Either one of those would be fine. I'm going to choose to use my cosine to find my sine because that's what you use the most. So to find my sine, I know that sine squared omega equals 1 minus cosine squared omega. And extracting roots, I know that the sine of omega equals plus or minus the square root of 1 minus cosine squared omega. Now let's decide whether the sine of omega will be a positive number or a negative number. Because omega is in the 4th quadrant, the sine function of angles whose terminal sides are in the 4th quadrant is negative. So we'll put our negative, and so we'll have 1 minus, and for the cosine squared of omega, let's put the square root of 5 over 3, and we want to square that. When we square the square root of 5, we get 5. When we square the 3, we get 9. So we'll have our minus. We'll write our 1 as 9 ninths. We'll subtract from that 5 ninths, and we will get our minus 4 ninths, and then the square root of 4 is 2, and the square root of 9 is 3. So we get the sign of omega is negative 2/3. Let's go ahead and write the cosecant of omega right up here. It is simply the reciprocal of negative 2/3, which is negative 3/2. So we have 4 of the functions. The other 2 functions that we need would be the tangent and the cotangent, and we could find the cotangent using the Pythagorean identity that relates. We could find the tangent by using the Pythagorean identity that relates the secant and the tangent, and we could find the cotangent by using the Pythagorean identity that relates the cosecant and the cotangent. But I'm going to choose to use the quotient identities for the tangent using my sine and my cosine. So let's remember what those quotient identities were. I know that the tangent of theta equals the sine of theta divided by the cosine of theta. I know the sine, and that is true, but what's my angle this time? It's omega, isn't it? So let's rewrite that. Let's see here. I know the tangent of omega equals the sine of omega divided by the cosine of omega. I know the sine of omega is negative 2/3. I'll divide that by the cosine of omega, which is square root of 5 over 3. Now, what I have here is a complex fraction, and I will simplify it. I know that for a fraction, when I divide fractions, I multiply by the reciprocal. So let's say negative 2/3 times the reciprocal of the square root of 5 over 3 would be 3 over the square root of 5. And of course, those 3's divide to 1. So what I get here is a minus, and then I'll have 2 divided by the square root of 5. Now what I need to do is rationalize that, and we'll do that by multiplying by the square root of 5 over the square root of 5. And we'll get minus 2 times the square root of 5 over 5. Now the last function I need is the cotangent of omega, and once again I could use the reciprocal here, I could use the reciprocal here, and that is probably what I would do. So let's see, the reciprocal of negative 2 over the square root of 5 would be minus the square root of 5 over 2. And that should be all 6 functions. Let's check here. Cosine, secant, sine, cosecant, tangent, cotangent, and of course those are the same values that we got using the XYR method. Now I've tried to emphasize in this lesson how to find all the trig functions either using XYR method or using the Pythagorean identities. After you have all 6 functions of an angle, go back and check. For that angle, two of those functions should be positive and 4 should be negative if that angle's terminal side is in the second, third, or fourth quadrant. So go back and check and make sure that you came out with 2 functions that were positive and 4 functions that were negative. Of course, if it's a first quadrant angle, all your functions should be positive. The other thing that you should check for is see if the numbers you got for your sine and cosine are numbers between -1 and 1, and see if the numbers you got for your cosecant and your secant are numbers greater than 1 or less than -1. Let's look at this last problem. Let's see here. Let's see what was positive. The cosine and the secant, and that's 2 functions, and those are the 2 functions that should be positive in the fourth quadrant. Look at your other functions. Your sine was negative, your cosecant was negative, the tangent was negative, and the cotangent was negative, and they should be negative for a fourth quadrant angle. Let's look at the values. Calculate that. 5 is approximately, the square root of 5 is approximately 2.2, and if you calculate that number, it's a number less than 1. And if you calculate this number, it's a number greater than 1. On the sine, obviously negative 2/3 is between -1 and 0, and -3/2 is -1.5, so that's less than -1. If you remember on your tangent and cotangent functions, we don't have a good check because those function values can equal to any real number. But after you get finished, it's a very long process, I know, and it's easy to get lost on your signs, particularly with your square roots and that sort of thing. But go back, and if the terminal side of that angle is in the second, third, or fourth quadrant, you make sure that you have 2 functions that are positive for that angle and 4 functions that are negative, and check the ranges of the sine, the cosine, and of the secant and the cosecant. It just takes practice. You'll be able to find all these function values. Just make sure that if you know one function value for an angle and the terminal side, the quadrant of its terminal side, that you can find all function values. This completes the lesson. Please rewind the tape. Thank you.